So everybody, thank you for joining us. I think we can get started. This is Blue SciCon, Blue Marble Space Science Conversations, and we're joined with Daniel Engerhausen. I hope I'm saying that correctly enough. I met Daniel 2 months ago at Goddard Space Flight Center. And Daniel invited me to give a talk to the Exoplanets Club, and that's how I got to know him. But Daniel's been involved in a number of different types of mission sensing, as he mentioned, his abstract sensing exoplanet atmospheres using prejudice, plane-based, and space-based methods. He's had his hands in a lot of different experimental, which has succeeded, some of which you maybe learned from techniques that were interesting, but maybe didn't pan out as much as you've liked. And I think that's actually a really great lesson, especially for all the students who are joining us. Everything in science doesn't have to be a Nature paper. Maybe sometimes you do, but science is about having fun, and it's about learning new techniques and trying things out. So Daniel is a postdoc currently at Goddard, moving to Switzerland very soon. So Daniel, please, the floor is yours, and love to hear about your research, and we'll probably have some questions during or at the end for you.
Yeah, perfect. So yeah, thanks for the introduction. I hope everyone can hear me, see my slides. I hope you can also see. So if the Earth is animated in that first slide, then hopefully also my animations are working. So let me know if that doesn't work. So I'm going to talk about how we sniff the atmospheres of exoplanets and eventually maybe even find something similar to Earth. But I want to start a little bit more general with that term astrobiology, also since I think that whole blue marble idea is more an astrobiological thing than just astrophysics. So I usually, when I give talks in an astrobiology context, I start with that old story or legend of the blind man and the elephant. So as the story goes, a handful of blind men find an elephant and try to figure out what that thing is. And you see the first guy is in the back and he's like, yeah, for me that looks like a rope with maybe a brush at the end. The second guy looks at the leg and thinks, yeah, that really feels more like a tree for me. And then the third guy touches the side and he's like, I'm not sure what you guys are looking at, but for me that's more like a rock or something bigger. And that's a nice analogy for what we are doing in astrobiology, I think, because we also have to connect these different fields of geology, biology, chemistry, astrophysics, and a couple of other fields to really have to zoom out of the context of our science to communicate with each other and understand this huge question of life in space. So we cannot really answer it alone in our fields, but really have to connect the different perspectives we get from our fields. And I'm going to focus most on this astrophysics side here, but I'm going to come back to this question a little bit later when we talk about biomarkers. So let's talk exoplanets. And exoplanets, it's actually a very old question. Even though we just found the first exoplanets about 25 years ago, it's already thousands of years ago that humanity started to ask this question. And it's maybe one of the oldest scientific questions, and maybe one of the biggest questions we have is, are there other worlds like ours, and are they different like ours, and how many stars and do also have planets? And great minds like Epicurus, Bruno, Newton, they all thought about these ideas, and it's really just in the last couple of years that we started to answer these questions. We even got amateurs finding planets nowadays. We find or maybe not find planets in our closest neighborhood. We find planets that are potentially habitable. With the help of the Kepler telescope, we double the number of exoplanets we know almost every year at the moment. We find really crazy planets like this Saturn on steroids, and find planets around stars where we never expected to find planets. So it's really our generation of scientists, astrophysicists that finally are able and have the technology to answer this really, really old question. And that's what personally excites me, to be honored, or to have the honor, or to be born at the right time to answer this question, which is one of the biggest in human history, I would say. So then you might ask why, oh wait, so this is just to give you an overview about what we know. Actually, this plot is almost a year ago, so I should update it. So this is, so we find so many of these exoplanets that we can put them in some sort of periodic tables and look at them statistically. We went from a exoplanet science where we were just analyzing and finding a handful of planets. We found so many that we can start putting them into a more statistical context. And here you can see it's basically a size. So you can see my cursor, right? So I guess yes. So it's an axis from basically Mercury size to Jupiter size, and then roughly divided in a hot zone, this Goldilocks, warm, potentially habitable zone, and a cold zone. And you can see that we find a lot of planets in this upper corner here, but that's mostly an observational bias. These hot planets and big planets are much easier to detect. And over the years, we pushed our detection limits into this direction, so downwards to the colder planets and smaller planets, and eventually even started to find these potentially habitable planets. And if you compare this to our solar system, so this is the same plot, same axis in our solar system, you see it's quite different, not only because of that observational bias, but we don't have any close-in giant planets, for example, in our solar system. Our solar system, it's the gas and ice giants are outside and the rocky planets are inside. And before we found the first exoplanets, everyone thought that is how planetary systems form. So we had to rethink that idea. Another really interesting thing is if you look at this super Terrans, between Earth and Neptune-sized planets, we don't have any of these in our solar system. But if you go back to the previous slide, this is actually the group where we almost find the most planets or the most exoplanets. So apparently, from this point of view, our solar system seems to be different from what we find out there. So we don't really have one of these super Terrans. Some people are theorizing that this planet X that was recently announced to be out there, or its impact is what was detected, that this might be one of these super Terrans. But bottom line here is our solar system might be quite different, or not like typical at least, to what we find out there. And we find a lot of stuff that we don't really know here, like these super Earth planets or hot Jupiters. So then you might ask, why is it so difficult? Why did it take us 3,000 years from formulating this question to finally answering this question? And the basic, really trivial answer is stars are larger than planets and stars are much brighter than planets. So if you look at this animation here, this is from the Jupiter transit just a couple of weeks ago. And if you see this tiny little dot here that you can barely see crossing over this huge stellar disk. I mean, it's admittedly like the smallest thing we still call a planet, but it still illustrates what challenges we are facing if we want to find these super tiny and faint planets next to relatively big and shiny and really luminous host stars. So usually the techniques we use to find them are indirect methods or methods that cancel out the stellar contributions. So indirect methods like the radial velocity method, where you measure the wobble or the gravitational pull and push that the planet does to the host star, or the transit methods, which you can see in this, which is also kind of shown in this animation. You see a planet transiting, and I'm going to come back to that later. Or even crazier methods like using a coronagraph and by brute force almost cancel out the stellar contribution and isolate the planetary signal. So these are roughly the approaches we need to use, or methods we need to use, to find information about these planets. Okay, so what I'm mostly working on is that differential photometry technique, sometimes also called the transit method, or mostly known as the transit method. So for some of these systems, we are happy or lucky enough that we can look at them edge on, and then you got, usually depending on the geometry, mostly these two phases. First, you got the primary transit, where the planet crosses in front of the stellar disks, and depending on the size ratio, the brightness of the star goes down, and then it does this orbit, and then in most of the times also disappears behind the star in a so-called secondary eclipse, where the light of the planet is missing while it's behind the star. And by observing these differences between the observations in and out of these occultations, we can reveal information about the planet. And a typical example how this data looks like is this one of the first, I think the second observation of a half-orbit light curve of HD 189,733. which is one of the gold standard benchmark hot Jupiters, one of the brightest host stars with a hot Jupiter, one of the best studied system. And in this case, it's a half orbit observation at 8 microns, so somewhere in the mid infrared with the Spitzer Space Telescope by Heather Knudsen. So what you can see here is this first big dip. So you got this baseline here, which is basically only the stellar contribution. Then you have this big dip here, about 2%. This is the primary transit. So this is the light of the star that is blocked by the planet. Then you got this line here, which is the orbit or half of the orbit of the planet. And then you got this somewhat smaller dip here. This is when the planet disappears behind the star. So this amount of light which is missing here are actually the photons of the planet that you're not detecting. So kind of like an indirect detection of the actual photons from the planet. But there's more to it. So if you look at this baseline in this, if you use these axes, it looks pretty flat. But if you zoom into it, you can actually see that there's a sinusoidal signal on top of that baseline. And this is actually the day side of the planet moving towards us. So this here is the primary transit again. Then you got this darkest time here. This is when you see the night side of the planet. And then as it moves on its orbit, more and more of the day side is facing towards us. So that's why this light curve goes up, because more and more of that reflective or emitting hot day side of the planet moves towards us. What's also interesting here is that you see that this peak of this phase curve is slightly before the secondary eclipse. So first order, we would assume that this peak happens right at the same time at the secondary eclipse, because that's when the substellar point passes behind it, and we assume that the hottest part should be the substellar point. But this actually shows us that the hottest point is somewhat shifted towards the east from the substellar point. So in a way, we can even use these phase curves to map the temperature contribution or the temperature maps of these exoplanets, which is kind of a neat thing to even get some sort of 2D maps of these planets just from these light curves. And these phase curves, it's one of the stuff that I'm working on. And a first example for the work that I did in this field was some research I did when I was at RPI in upstate New York. Actually, with my undergrad student, Emerson Del Arm at that time, who won an undergrad research competition and was invited to present that work here in Washington at Capitol Hill. So what we did in this work was we used data from the Kepler Space Telescope and fitted a couple of these phase curves. So what you can see here are really, for a couple of Kepler planets, these phase curves. So all these dips in the center are actually secondary eclipses. And these curves in between of it are the phase curves. So the day side, mostly the day side contribution, but also a couple of stellar models we had to model at the same time. So we did that for about 20 planets in the Kepler data set, and were able to derive brightness temperatures, albedos, and even night side temperatures for some of these planets. So this was the first time that such a big group of planets was analyzed in a consistent and comprehensive way to derive these parameters. And if you get a certain number of parameters for somewhat larger group of objects, you can also start trying to see if there's any correlations. And one example, what we try to figure out is this plot. So you can see here, this is the albedo on the y-axis versus the incoming flux of the planet. Then we also color coded the metallicity of the system in our tick marks, and also the log G of the host star and the size of our symbols. And you can see there doesn't really seem to be any correlation. So it's not that the planets that get a high flux have a higher albedo, or that the ones which have a higher metallicity are more reflective. So it's really, that doesn't really seem to be any correlation of the albedo with any of these parameters. The only thing we can really see, if you look at this comparison, the line up here is Jupiter, which has an albedo, so kind of like a grayscale color of 0.5. So it's reflecting almost as much as it's absorbing. If you compare that to the hot Jupiters, they are really much lower in albedo, at least in these optical bands. And That might be somewhat counterintuitive for many of us, because if you assume they are hot, you first of all would think they are maybe like also like a white glowing or hot glowing, but in fact they are actually pretty dark, almost charcoal dark with very low albedos. And that's one of the things we are trying to figure out, why actually the albedo of these hot Jupiters is so low in comparison to, for example, Jupiter. Might have to do with clouds or the or no presence of clouds. So we are still, that's one of the questions we are trying to answer right now. Another project that I'm working on in this context of phase curves was also a work with a student at that time, Ben Plesek. I was a part of his PhD committee. He um, he built a code called ExoNest, which is a Bayesian phase curve modeling and retrieval code. So these exoplanet phase curve have a lot of parameters, and many of them are quite degenerate. For example, you could have like a hot planet or high reflective planet. So sometimes the emission and the reflection of a planet is highly degenerate. So, and in order to disentangle these degenerate models, it's always nice to have a Bayesian approach, because that helps to at least illustrate these degeneracies. And so in the meantime, we actually use this code for a couple of other things like exomoons, not only the phase curves exomoons. We had we modeled what we could do if we combine photometry from two different platforms like Kepler and TESS. So it's a really versatile, nice Bayesian nested sampling algorithm to work on these phase curves. And this is just an example. For example, in this case, we have a ellipsoidal, an eccentric phase curve versus a non-eccentric phase curve, and by modeling it, we could show that this system, I think in this case it was HUT7, actually has an eccentric orbit and not a circular orbit. Just as an example for what you can use ExoNest with. Another really neat application of these phase curves is another work which I did with Michael Hipke last year. Is we were looking for Trojans. So some of you might have heard about the Trojans in Jupiter's orbit. So you have a system. If you have a system of a star and a planet, there are a couple of so-called Lagrange points in the system where that are gravitationally stable. And in this case, this is L4 and L5, so Lagrange point 4 and Lagrange point 5, which kind of act like a cosmic trash dump. So because they are gravitationally stable, stuff gets trapped in there. So all the remnants from planetary formation, all the rocks that didn't build planets in the end, collect in these spaces over time. And Jupiter has roughly like or is theorized to have roughly like 1 million kilometer-sized objects trapped in these Lagrange points. And the cool thing about these Lagrange points is no matter what system you're looking at, if it's a 6-day orbit or a 600-day orbit, they are also at the same part or at the same place in the phase, in the orbit or in the phase of this planet. So that means if you look at many planets, these Trojans should be at the same phase. And these Trojans are too small to be seen in one single light curve alone. So you really cannot. It's probably impossible to see Trojans like that transiting in a single orbit. So you would expect to have these dips left and right of this central transit right in these Lagrange points. But the idea that we had was, if we phase fold all the planets from the Kepler dataset on top of each other, we could actually suppress the signal to noise so far down that we might be able to at least find a statistical signature of these Trojans. And that's in short what we did in this paper. Also got a nice little New Scientist press release. So here we really took about I think it was like, in the end, it was like 2,000 Kepler planets and about 90,000 phase curves that we all folded on top of each other. And then we actually found these tiny dips and also a couple of other evidences, but this is the money plot from this paper. These little dips in the Lagrange points where we expected. In the center, you see the primary transit. The flux axis is really in parts per million. So this is really just 2 parts per million in these light curves that we can detect here, these dips symmetrically in L4 and L5. And since this is only like a 2-3 sigma detection, we didn't want to call it the a clear detection of these Trojans, but there are really many evidences that point that these Trojans also exist around exoplanets. And it's not like a crazy claim because we have Trojans all over the solar system. So one should assume that these are also present in extrasolar systems. So another nice application of these phase curves. Um, so all the stuff that I showed so far was work with the Kepler Space Telescope. So really just in one color, one photometric channel to observe these transits, eclipses, and phase curves. But obviously, it's much more interesting and bears a whole dimension more of information if you do that stuff in a spectroscopic way. So observe these transits or eclipse at many colors or many wavelengths, preferably at the same time. And this is an example again, Heather Newton's work with the Hubble Space Telescope. And then again, you can go into primary transit and look at the extra absorption of that outer layer of the atmosphere. So you can imagine if this planet crosses in front of the star, the starlight falls through that outer terminator region of the planet, and then depending on the material here, the transit light curves that get deeper or shallower if there's something that absorbs or nothing that absorbs. And the broadband depth of that primary transits, at least for Jupiter, is about 3%. But the spectral features, so the difference between something absorbing in the terminator versus the continuum, is a few 10 to the minus 4, so a factor of 10 smaller than the actual depth. Then you can also do these observations in secondary eclipse where you probe the day side, so that emission that is coming from deep inside of, or deeper than this terminator region, from deep inside of the day side of the planet, disappearing behind the star. And in this case, as we have seen in this phase curve I showed before, the depth is about a factor 10 smaller, so a fraction of a percent usually. But the spectral features, so the difference between, let's say, a methane emission feature on the stellar atmosphere versus the continuum, is also 10 to the minus 4. So in terms of the signal to noise we have to reach is actually the same challenge. Even though the primary eclipse is, or the primary transit is deeper than the secondary eclipse, it's still the same challenge in terms of signal to noise to observe primary transit or secondary eclipses. And in practice, it works like this. Then this is an example from a day-side observation of HD 209, another hot Jupiter with the old Hubble NICMOS instrument. And in this case, each of these transit light curves, or in this case, eclipse light curves, represent the spectral value at the corresponding wavelength. So each of these black crosses here represents the depth of the secondary eclipse at that wavelength. And at that time, in 2009, we asked our colleagues that do planetary exoplanet models to just see if they can model this. So first they started with a model that just contains water, and we got this purple line here, which didn't really fit the data. Then they put methane into the mixture. We got the green curve, which kind of fitted better, but in this area didn't really work. And just as they added CO2 to the mixture, we got something like the orange model, which kind of looks like it fits our data. And this is also an area of exoplanet science which really evolved over the past 10 years. So it's really coming from this comparison with forward models in this example to very sophisticated Bayesian methods where people throw a million models at these data and then really can constrain not only qualitatively but also quantitatively the abundances and temperature pressure profiles of these exoplanets. So this whole comparison thing here is at least another whole talk on its own, which I can't go into so much detail right now. And the questions we can answer right now. So the question is, with the available telescopes we have right now, ground-based telescopes like Keck and VLT and mostly Spitzer and HST in space, what are the things we can already answer with these questions? And as I mentioned before, the easiest targets for these observations are the hot Jupiters. Those are really big Jupiter-sized planets and really close in to their host star. That means they are hot, they have frequent transits we can observe, they have larger signals because they have higher infrared fluxes. So they are just the easiest and therefore obviously the first targets to focus on. And we can answer questions like, for example, how, since most of them are tightly locked and always showing the same side to their host star, they got a really hot day side and a relatively cold, in comparison, cold night side. And one of the questions, for example, is how does the heat get transported from the day to the night side? Are there any winds, any other exchanges that can transport the energy to the night side? Some questions about, are they evaporating? Is the star blowing material away from the planet, or is there even material falling in from the planet to the star? Then also questions like, how did these hot Jupiters even get so close to their host star? Because planetary formation tells us that they can't really form that close in. So that whole question about how did these hot Jupiters migrate there, these are all questions we can tackle right now with the existing technology that we have. And one picture book example is this observation of WASP 43b, one of the hottest Jupiters we know, or Jupiter exoplanets we know, that was observed with 61 orbits with the HST Wide-Field Camera 3 um, instrument by Kevin Stevenson. That it's not my work, but I think it's really like one of the coolest things we have done in this field so far. So you can see here on the top, it's the emission spectrum of the planet depending on the phase. So this is the night side here, and then it goes up and up and up until you see the day side spectrum at 0.5, and then it goes back down to the night side spectrum, which is pretty flat here. And then you can also see the thermal profile. So the basically temperature versus height, or temperature versus pressure of this planet, depending on what side of the planet or which phase of the planet you look at. And then on the bottom, you can even see brightness temperature maps, as I described before, at different wavelengths. So in the center is this water band, and then left and right of it. So you can even get a distribution of the heat in different wavelengths with these observations. And this just gives us a glimpse at what's going to be possible in the future. So these observations with Hubble on really hot Jupiters might also be able to do it with the upcoming James Webb Space Telescope for smaller planets and colder planets. And it would be really nice to get these observations maybe for somewhat colder Neptune-like planet, or maybe even a super Earth. So this really is just the first time we see something, and in the future we might be able to do that stuff for many other planets than just WASP 43b. Another thing we are working on right now, or able to work on right now, is this whole super Earth versus mini Neptune question. So I mentioned before that we found this huge class of planets which we don't have an analog in our solar system. So one of the questions is, where is the transition between like a big rocky planet and a small gas or ice giant? And right now we are not sure if it's even like a fixed boundary, or if it's like a transition region. So that's one of the things we want to figure out, especially with regard to potentially habitable planets. We want to know, which ones are rocky planets, because we don't think that ice or gas giants are that good for life. So this is another question we are able to answer, at least for some really close by exoplanets of these classes, to see what they are made of, or if they are more on Earth or more on Neptune. And in the future, the big goal, coming back to that big question I asked in the beginning, is of course to eventually find life on these other planets, and maybe even with this transit or eclipse spectroscopy to see these fingerprints of life. Here you can see a transmission spectrum of Earth, for example, with the ozone, water, CO2 signatures, which we call potential biomarkers, so fingerprints in the spectrum that we think can only be made by life. And the most promising right now, if you trust, the atmospheric modelers and the biologists, is oxygen and methane. So if you find oxygen and methane at the same time in the planetary atmosphere, we think that this is a smoking gun for life. And some of our colleagues always compare it to grad students and pizza. So if you have grad students and pizza in the same room, the grad students eat the pizza. So it's highly unlikely to find both at the same time um, in the room at the same time, unless something just produced the pizza, or unless someone just delivered the pizza. And it's the same thing in the planetary atmosphere. If you find oxygen and methane at the same time, you need something that constantly delivers both of these both of these both of these. So if you find both at the same time, there is probably life in play that keeps resupplying either of the two. But this is really the future. So this might not even be able. We might not even be able to do that yet with James Webb. So you probably have to wait for the next generation, the next big telescope after James Webb to do that kind of science, or maybe a dedicated mission to do that. So that brings me actually back from the future to the past where I started, and this is what Jacob meant in the beginning. So, oh no, wait. So I forgot this one. So um, in this whole biomarkers discussion, it's also important to realize that the atmosphere is not just the biosphere. So we got all these, we got volcanism, we got the interaction between the ocean and the atmosphere, we got high altitude photochemistry going on, we got interaction between the ice and the atmosphere, we got all kinds of geothermal cycles going on. So our atmosphere is really more complicated than just the biosphere. So there's all these interactions going on here. And this is actually an example for that elephant that I mentioned in the beginning. So we really need input from all these different fields, from geologists, from atmospheric chemistry. We even use Earth climate models to really get a grip on this question: what is a good biomarker, and are there no abiotic sources, for example, oxygen and methane? So this is really one of these fields where we have to work interdisciplinary to answer that question. Okay, but now we go back to the past and how I started. So in the beginning of my career, we were hopeful to do these observations also from the ground. So what I presented so far is Hubble, Kepler, Spitzer, all observations with space telescopes, because observing quality is much better up there. But on the other hand, it's also much more expensive to observe from up there, and it's also much more competitive. So I think the last Hubble call, for example, was 20 times oversubscribed, and even some proposals that were rated excellent, they weren't able to observe them. So it's really hard to get that time on space telescopes, even if it's a really awesome project. So it would be really nice also to take pressure off these space-based telescopes if we can do these observations also from the ground. And that's what I spent most of my early career with. I had to go to Hawaii and Chile and do these observations and try some things out with various instruments we had available at that time. It didn't really work out well, so I mostly just published conference proceedings that said we tried it, but it didn't work out because that one thing didn't work, or because our atmosphere was too disturbing, things like that. And it is really just in the last 2 years that we might have some new hope, because two new so-called multi-object spectrometers got installed at Keck and the VLT. And I want to just skip through that slide because it's quite technical. So the bottom line here is that we got these instruments that enable us to observe spectra of many stars at the same time. And that means we can observe our star that has a transit and a comparison star at the same time, and then can cancel out our atmospheric transmission, or the changes in our atmospheric transmission, which is usually the biggest problem from the ground. And I think that's all that I want to say. For that example observation with KMOS, you can see from the plots it's complicated, and that's probably the message you should take. It's really complicated instruments, and it's quite some effort to do these observations. Just as an example how hard it is, not even from the instrument side, is that observation with KMOS at the VLT. So I heard about that instrument quite a while ago, and once it was installed, I submitted a so-called science verification proposal. So before an instrument goes into real operations, you can submit these ideas, what science you can use it for. So we got that one accepted. We got a transit observation of GJ 1214b, which is one of these super Earths, but we had technical issues, so it didn't really work out. Then I went there in person in 2014 for 2 more nights, and the first night we had bad wind speeds. So the wind was very strong from one direction, and that was exactly the direction where my target star was. So I could have pointed everywhere else in the sky, but not that direction. And then the second night, maybe some of you remember these pictures from the Atacama Desert where it rained for the first time in 5 years and everywhere these flowers started to bloom. That was actually that night that I observed. So it rains in the Atacama Desert one night in 5 years, but just that one night where I was observing. So this didn't work out either. And then I went again last year, and the first night we had a power failure, and our instrument warmed up, and we couldn't cool it down in time. So again, it didn't work out, and it was just in the sixth attempt later that year that we finally got our data. And this kind of illustrates how tricky it is to do these observations from the ground. And so then if you know that it works from space, but it's really tricky from the ground, why not go somewhere in the middle of it? And this is where Sophia comes into play. So if you are tired of these ground-based observations but can't really go to space, why not put a telescope on a plane? And this is what you can see here. Sophia really a 747 aircraft with a 2.5-meter telescope in the back of it. So you got this basically garage door on the back that opens and then exposes the telescope right to the right up there in the atmosphere, in the stratosphere. It's a NASA and German space agency collaboration. Sophia observes at around 40,000 feet, so a little bit higher than commercial airplanes. Right now, it's equipped with 7 imagers and spectrographs that cover really the whole wavelength regime from the optical to the very far infrared. And it's supposed to operate for the next 20 years with 120 nights per year. And a couple of milestones in '07, the first test flight of the observatory. In '09, the first open door flight. That's the video you're watching. And then in May 2010, the first light, so the first astronomical observation. And then since 2011, it's in normal science operations, and everyone who's interested to use it can just submit proposals to observe with Sophia like with any other telescope. And for these particular transit observations that I'm working on, there are a couple of advantages for Sophia. It works in the wide wavelength regime. It's a mobile platform. It has less atmosphere that absorbs. And the cool thing is also you can put dedicated instrumentation on board of it. So unlike the Hubble Space Telescope, where you have to send a dangerous and really costly space shuttle mission to replace instruments, Sophia is basically a space telescope that comes home every morning. So you can really put the newest detectors, the coolest instrument right on Sophia and bring them in a quasi space-based environment every night. So this is a cool advantage of Sophia. And after a couple of attempts, finally in October 2013, I got my first test flight or the first transit observation with Flippo and with Flippo. That's this flight cam and Hippo. So in an infrared camera and the optical camera, we observed the transit of HD1 at night 733b. As I mentioned before, one of these standard benchmark or Jupiters, and this is the first light curve observed with Sophia. So for those of you who might do these transit observations, you see it's a really clean light curve. We didn't need a comparison star, which is usually only possible from space. So this is really what we call space-based quality, which immediately proved that Sophia is more like a space telescope than a ground telescope for these kind of observations. And if you compare it to other space telescopes, in this case Hubble and Spitzer, if you compare our error bars, so the precision we can get, we are already getting really close to the space-based telescope in comparison. So bottom line, Sophia is really almost a space telescope. And there are a couple of problems with Sophia. So one problem is we need to point at our targets for at least a couple of hours. And here you can see a typical flight plan of Sophia. So we have to start in Palmdale, California, and have to return here. And so that means, and since the opening of the telescope is only on one side, you can only point in one direction roughly for half of the flight. So if we need to observe a 2 or 3 hour transit, I need an hour before and after. It's really tricky to schedule this one long leg that we had here to point at that transit at that particular point of time. And also another constraint is that we have to land in Palm there before sunrise. You can see here it's getting lighter. Here you can see it gets lighter. That's when when sun rises, and we have to land before sunrise because NASA is scared that we can't close our door and then sunlight falls into the mirror and burns the telescope, burns the plane from inside. So this is another constraint. So in practice, these flight planning constraints make it really tricky to do these observations with Sophia. The instruments are not very well suited because they are quite of age and not really designed to observe transits. They're more designed to observe faint galaxies, for example, or faint dust and not really bright exoplanet host stars. And there's also huge competition with mid-infrared and far infrared observations on Sophia because that's where Sophia is really exclusive. So that makes it hard for us to actually get time for Sophia in practice. So bottom line, in theory, there are a couple of advantages and there might be a few niche science cases for Sophia, but it will probably not become a workhorse in this field for a long time, especially since James Webb is going to do most of these observations. And this brings me to the end of my talk and the future, what's going to be there in the next 5 to 10 years. There are a few missions, two of them, Cheops, a Swiss-led mission, and TESS, that are dedicated for exoplanet characterization and detection. And then everyone is waiting for the James Webb Space Telescope, which is the next big thing, the next generation flagship mission, as we call them here at NASA. So basically, the Hubble Space Telescope for the next generation. Um, and that's the stuff that I'm working on right now. TESS, for example, is supposed to find the brightest transiting planets in our neighborhood, which then James Webb can follow up and analyze the atmosphere, as I described before, by transit, eclipses, and phase curves. And one of the problems is that TESS and Cheops also work almost around the same time that James Webb gets launched. So one of the real problems for us is to get all this traffic of potential planets found with TESS and Cheops confirmed and pre-characterized in order to find the best targets to observe with James Webb. And this is what I illustrate here. So we really have to, over the next few years, have to figure out the right strategy to get the interesting targets on the fast lane and maybe the boring hot Jupiters on a detour to really focus on the best targets to get them to James Webb as fast as possible. And just to summarize, that is taken from a slide from Ricker, who is the PI of the TESS telescope. Roughly a summary of the science we probably be able to do in the combination of James Webb and TESS. So we probably be able to answer this whole question about whether or not Jupiters, as I mentioned before, how does the heat distribute on the surface of these planets, how did they form, how did they migrate there, also for like somewhat smaller planets like Neptune's. And we might even be able to get to some of these super Earth planets and at least check for signs of habitability. So at least check if there's water present and how many of them have water present. So this is realistically what we can do in the next 5 to 10 years with the combination of James Webb and TESS. And that actually brings me to the end of my talk. And I usually have this video on YouTube that I did during my Sophia observations, and I usually just let that video run while we do a question and answer session. So thank you for your attention.
Thank you much. Thank you very much, Daniel. That was really enjoyable. And so the floor is now open for questions. Anybody has questions, you can feel free to unmute your microphone and ask Daniel directly. You feel free to type it into the chat box as well, and I'll be happy to read it out.
So I have a question. Hi, Daniel. This is Sanjoy. Thank you very much for your very nice presentation. I was wondering how the signatures, the spectral signatures from exoplanets are affected by the local air pressure on these exoplanets.
You mean the pressure on the planet itself, or?
Yes.
I mean, these all go into these. So when I describe these models, or the people who do these forward model or spectral retrieval, they usually use temperature pressure profiles for these exoplanets. So this is one of the input parameters for their spectral retrieval. So they assume a certain altitude distribution or temperature pressure profile, also depending on day side and night side, or maybe a little bit more sophisticated 3D models. And then that becomes input for their chemistry, for their radiative transfer models. So it basically goes into these atmospheric models.
So if the air pressure on those exoplanets was a lot less or a lot more, would that affect the spectral signature?
Oh yes, of course, yeah.
Oh, okay.
So I mean, one thing it's always temperature pressure, right? So if you go to lower pressures, it's thermodynamics. So one thing, for example, is we think when temperatures go from, let's say, 1500 K to below or below or over 1500 K, we go from CO2 chemistry to methane chemistry, for example. Or if we go to even higher temperatures, we expect to find titanium oxide in the upper atmosphere of these planets. So it's definitely temperature and pressure driven, these planets, these planetary spectra. Yeah.
And is there a way to measure air pressure using spectral signatures?
I mean, usually these temperature pressure profiles are a result of our fit. So we find the best fit temperature pressure profile if we do our spectral retrieval. So that's probably the only thing we get, because also at different wavelengths you look deeper into the atmosphere. So for example, in the optical you look at the highest cloud layer, whereas in the infrared you look deeper into the planet. So you always get the pressure at that certain height, or the temperature as that certain height, which then again translates into pressure, if that makes sense.
Cool. Well, thank you.
Any other questions from anybody? I guess the one question I'll ask is, what are you planning on working on when you get to Bern?
Oh, just a second. So right now you can probably see the telescope moving in the video. I'm not sure if you see that. So this is actually, so it looks like the telescope is moving, but it's actually the telescope is staying completely pointed on the star, and it's really just the plane moving around the telescope. That's a cool thing. So so it's all inertia that keeps or mostly inertia that keeps the telescope pointed at the star, and all the stuff around it is actually vibration and movement of the plane that the telescope is compensating.
Wow. That explains why riding a plane can make people motion sick.
Yeah. Actually, on Sophia, the telescope takes over the autopilot while we're observing, because we cannot really point the telescope because it's just pointing out of the side. So all the pointing has to be done by navigating the plane, actually, and that's why the telescope takes over the autopilot while we are flying and observing. To come back to your question, I'm going to be working with Kevin Heng and Brice Demory at Bern, Switzerland. So one of the big things, obviously, is going to prepare for James Webb and Cheops. So Bern is also a big partner in the Cheops mission. So I'll probably be working on Cheops data reduction or Cheops data. And then we mostly want to focus on these exoplanet phase curves, maybe for smaller planets, see if we can also, if we can optimize these phase curve observations. One thing I'm working on right now is if we really need to observe the whole orbit, or if it is enough to observe a little bit before and after transit and a little bit before and after eclipse and still get the full information of the phase curves. So that's some of the stuff that I'm working on right now. So mostly optimizing and figuring out the best strategy how to use James Webb, basically.
Oh, that's great. Well, every now and then we'll email Kevin Heng, and we've collaborated with him on a couple projects, so that might be a good opportunity for us to stay in touch too.
Yeah, definitely.
There's a question from Shaylin in the chat. She just asks, how much information about a distant planet can you gather from analyzing its transit? So I guess what key position can come out of a transit? And I guess that could be both spectrally and non-spectrally.
So the cool thing, if you find an exoplanet with a transit, is first of all you pretty much know the inclination, because it has to cross in front of the star, right? So it's really an inclination between 85 and 95 degree maybe, which then again allows us to do radial velocity observations and become a mass. So we immediately get the mass of the planet from radial velocity, and we get the radius of the planet just from basically the size or the depth of the transit. So a planet with a bigger radius does a deeper transit, and a planet with a smaller radius has a shallower transit. And then if you get mass and radius, you can immediately derive the density, for example. So this is a huge advantage. If you have transiting planets, you can get a density for these. And that helps us again to figure out if it's more like a rocky planet or a gas planet, because gas planets are lower in density than these rocky planets. That's one thing. Then the other thing, it really enables us to see these transmission and emission spectra, which is not really possible for any other detection or the other detected exoplanets. So there's really an advantage for these transiting exoplanets in that area, if that answers the question.
Perfect. I think, yeah, perfect. That was great. And then there's a question from Ryan here. He says, last year, an occultation of Pluto was captured by Sophia in the South Pacific, starlight through Pluto. Were results able to be gathered from that?
Yeah, that was a really yeah, that was one of the coolest things that Sophia did, I think. So sometimes Pluto occults a background star. So it's almost the same setup as these planetary transits. So you got a star in the background, and then Pluto moves in front of it and basically covers it completely. And similar to, for example, like a total solar eclipse, where you have a shadow the size of the moon on the Earth's surface, you have a shadow the size of Pluto on the Earth's surface. And it's really unlikely, or it's really, you have to be really lucky to have this shadow moving over some ground-based telescope. So it really just happens once in a blue moon that you see one of these Pluto occultations from Hawaii and Chile. And that's the cool thing about Sophia. You can basically fly Sophia into the shadow of Pluto, and that's what the folks did. So we got people at MIT who were constantly calculating the telemetry and figuring out where the shadow of Pluto was in real time. And then we got our pilots on Sophia flying actually on the South Pacific into an area as big as Pluto, fly into Pluto's shadow. And the cool thing for that observation was that it was like a week before New Horizon arrived, which means now we have an observation from Earth of one of these Pluto occultations that we can connect to the data that New Horizon took in situ, or almost in situ at Pluto, which is like an awesome, almost like a Rosetta Stone for comparing future observations from Earth of Pluto occultations to what's actually happening there. And that's why that observation of Sophia was so important for Pluto, or for that kind of science.
Thank you. And Ryan actually has another question. What other works and results do the Hawaii and Chile telescopes produce via exoplanets? How many exoplanetary scientists are there?
So Keck, for example, is a really big workhorse in radio velocity. So there's the HARPS instrument on, I think, the Keck 1 instrument. And I might be, but I think about 50% of the time on Keck, sometimes it's really for these radio velocity follow-up or confirmation of these planets. So there's a lot of radio velocity stuff going on. Not so much that transit spectroscopy things, for the reasons that I mentioned, because the atmosphere it's really hard. I mean, you basically observe, you try to find water, methane, CO2 in these exoplanet atmosphere and look through all the atmosphere of water, methane, and CO2 that we have here. So it's really like, looking through pink sunglasses and trying to decipher two different colors of pink. So it's really, really hard to do that from the ground. But so it's mostly in this high spectral resolution regime, because these instruments usually don't fly in space, because high resolution spectrographs are really hard to maintain in space. So everything that needs a high spectral resolution so radio velocity observations, also cross correlation observations like Ignaz Snellen from Leiden is doing, these kinds of observations are really the driver in exoplanet science from the ground right now. And then some folks like me who try to misuse some of the existing instruments for exoplanet science. That's what I mentioned with Sophia. Some of the instruments are really not, or most of the instruments are not built for that science case. So most of the instruments are built to look at faint objects for a long period of time, and are not built to be stable over hours as we need it. So that means sometimes we have to do crazy things, like some people, for example, when we go to Keck, we ask the telescope operators to defocus the telescope, and they think we are crazy because no one builds a 10-meter telescope to get highest spectral resolution and then defocus it again. So in a sense, we transit observers are kind of like the crazy dudes who really really tweak the existing instruments for our purposes because they're not built for it.
All right, thanks. And we're getting close to the end of the hour, but Brian's got one more question. So would it be interesting to send humans toward the Lagrange points, and should it be a goal to send humans there? And that might actually be a fun question to end on, too.
I mean, one nice application would be we could service the James Webb Space Telescope, right? So James Webb Space Telescope is going to L2, so the other Lagrange point behind Earth. So if you draw a line from the sun to the Earth and then farther out, so basically in the shadow of Earth, James Webb is going to be there. And it would be kind of nice to send astronauts there to update or maintain or refurbish James Webb, just as we did with HST. So that would be definitely a nice application. But we probably also be able to do that with robots. And as a matter of fact, probably people are already looking into it just to make sure we can rescue James Webb if something goes wrong. In general, I think it might be. I mean, there are a couple of places where it might be good to do the first human outpost, if you want so. So I mean, it's obviously we not want to get everything all the time from Earth there. So it might be good to maybe start with a base on the moon, but it might also be might have some advantages to start with some base in the Lagrange point. So might be one of the next milestones in human exploration to build some kind of station in the Lagrange points, but maybe not in the next 5 years, but maybe in 10.
Ryan, I'll actually mention that several decades ago, the L2 Society was actually interested in this very question of setting up a space station at L2, and that organization has now become the Planetary Society, I believe. So,
oh, interesting! I didn't.
There's still some interest in those questions, although they've a little bit more. Daniel, this has been a really great conversation. Thanks so much for your time. I think we all really enjoyed this. It's been a great overview of exoplanet science as well as your particular projects, which I really like hearing about how you push the bounds of some of this technology and try to use it to do new science. And definitely got some really cool stuff out of it. So thank you once again. It's been a pleasure.
Yeah, thanks for having me. And if you have more questions, don't hesitate. Just write me. You got my email, right?
Absolutely. I'll be sure to send it to everybody.
Okay, cool. Thank you. Bye-bye.